Hi folks, Chris McClure here. We now turn our attention to section 4.5, where we will continue talking about using the multiplication rule to compute the probability, but using the complement rule and some more about the conditional probability computation. Okay? So the complement rule is going to be used to help us compute an at least one type of probability. And we'll take a look at computing the conditional probability, which, by the way, we started talking about last time, but in a more theoretical context. Okay, we'll come back to the conditional probability a little bit later, but let's focus on complement. What does it mean to take the complement of an event? That means that the event doesn't happen. Okay, that's what the complement means. When we say at least once, that means 1, 2, 3, or 4, or 5, or more times, not 0 times. So when we say at least 1, that's the complement of none. Okay, so it's important to understand both of those concepts. To find the probability of at least one of something, then that'll be 1 minus the probability that none of those things happened. Because of the fact that the event of at least one thing happening is the complement of the event that nothing happens. So in your mental model, think about a coin flip. You flip a coin 50 times. The event that you get at least one head out of 50 coin flip is the complement of the event that you get 50 tails in a row and 0 heads. So if we want to calculate the probability of getting at least one head, that'll be 1 minus the probability of getting 0 heads. And it's a lot easier for us to calculate getting 0 heads than to calculate getting at least 1 heads directly. So we'll calculate the probability of getting 0 heads and subtract from 1 to calculate the probability of getting at least 1 heads. So here's another example besides the coin flip. Suppose that we have this company, Topford, who supplies these X data DVDs. And they're supplied in lots of 50s. And they have reported a defect rate of 0.5%. In other words, every 1,000 DVDs that come off the assembly line, 5 of them will be defective. So that means that if you were to randomly select a DVD as it comes off the assembly line, there's a 99.5% chance that it'll be good. So suppose that we were to take a random sample of 50 DVDs from the assembly line. What's the probability that at least one of those DVDs is defective? And what we mean by at least one is that either 1 is defective, or 2 is defective, 3 are defective, 4, 5, 50. And as we will see, the probability of having at least one defective disc in 50 is going to be 1 minus the probability that all 50 discs are good. Because all 50 discs are good is the complement of the event that at least one disc is defective. Now, the probability that all 50 discs are good means that the first disc is good, which has a probability of 0.995, and the second disc is good, which also has a probability of 0.995, and so forth. And by the way, each of those individual events or outcomes that the DVD is good is independent of any other disc being good. So you want to calculate the probability of having 50 good disks. Is 0.995 times 0.995 times ... 50 times. In other words, you're going to take 0.995 raised to the 50th power. 0.995 raised to the 50th power is the probability of having 50 good disks. Subtract that from 1, and you'll end up with 0.222. Go ahead and try this on your calculator. So what we conclude is that if we randomly sample 50 DVDs from the assembly line, the probability of there being at least one of those disks being defective is about 0.222. About a 22.2% chance at least one of those disks out of 50 will be defective. Okay? So that's an example of using the at least once rule that uses the complement rule. Now, we will return to our discussion of conditional probability. As we talked about last time, conditional probability talks to the ideal of conditioning one event on the outcome of some other sort of trial or experiment. So remember, talked about, for example, the drawing of 2 cards from the deck of 52 playing cards. And we wanted to calculate the probability that you draw 2 spades in a row. First card's a spade, and you hold on to that card, and then you have 51 cards left. And knowing the fact that that first card is a spade will allow us to calculate the probability of the second card. We know that the probability that the first card is a spade is 1/4. And then you want to calculate the probability of getting the first card of spade, and given the fact that the first card is a spade, that the second card is a spade. Well, with the second draw, 12 of the cards out of 51 will be spades, so there's a 12/51 chance that the second card is a spade, given the fact that the first card is a spade. This probability that the second card is a spade, given the fact that the first card is a spade, is an example of conditional probability. We're doing some conditioning on the outcomes of some previous experiment. So that's what we're saying here. Conditional probability of an event is a probability obtained with the additional information that some other event has already occurred. So, for example, probability of event B given event A. So probability of B given A, this little vertical line segment means given. Probability of B given A denotes the conditional probability of event B occurring given that event A has already occurred. And it can be found by, one way of doing it is dividing the probability of events A and B both occurring by event A. And likewise, the probability of A given B is equal to the probability of A and B divided by the probability of B. So you see this second event here, the event that we're conditioning on, you'll see the probability of it in the denominator of that calculation there. And I just want to remind you, this is one way of calculating this conditional probability of B given A here, or A given B here. This is not the only way of calculating the conditional probability. We can use an intuitive approach, just like we did with the cards. And let's just go ahead and read this. The conditional probability of B given A can be found by assuming that the event A has occurred. For example, that we drew a spade as our first card, and then calculating the probability that event B will occur. So the probability that the second card is a spade, given the fact that the first card is a spade, was 12 over 51. That's the intuitive approach. So here's an example. Suppose that we were to randomly sample 1,000 people and subject them to a drug test. Ask them to do a urinalysis, for example. Well, suppose that we know that 50 individuals in that population are drug users, and then that the other 950 are not drug users. Also, suppose that 134, add these two right here, 134 people come up positive on the drug test. And then 6 plus 860 is 866 people test negative. Add this row, you get 50. Add this row, you get 950. So we got row totals and column totals. By the way, this is an example of a two-way table, because of the fact that we've got two variables in play here. We've got the variable as to whether the subject uses drugs or not, and the other variable as to whether the test came back positive or negative. And then the intersection of a column with a row will give us a number of the individuals who will tested positive or negative and use subject or use drugs or not drugs. So there's 44 individuals who tested positive and used drugs. So you can think about this 44 as being at the intersection of the event that the subject used drugs and the event that the test came back positive. Or the 860 is the number of individuals who both tested negative but did not use drugs. All right, so let's answer a question. Find the probability that a subject actually uses drugs. So take a look at this row right here. Given that he or she had a test positive, a positive test result. Now, when we condition on the fact that the test came back positive, what that really does in reality is it focuses our sample space to just the set of all individuals who tested positive. And there were 134 people who tested positive. And of the people who tested positive, of the 134 people who tested positive, there were how many individuals who actually used drugs? Well, 44. So the probability that we're actually looking for, this conditional probability, is actually going to be computed as 44 out of 134. That's a straightforward way of calculating this conditional probability. 44 out of 134. Now, if you wanted to strictly use the formula that you saw on the previous slide, then you can use this calculation. That's that the probability that the subject uses drugs given the fact that the subject tests positive. Well, using that formula, that will be the probability that the subject both uses drugs and the subject tests positive. And that probability is going to be 44 out of the 100, or excuse me, out of the 1,000. 44 divided by 1,000. That's the probability for this first event and the second event. So the word "and" means intersection. So there's 44 individuals at the intersection of those two events. And then divided by the probability that the subject tests positive. And of course, there were 134 people who tested positive, so there's a probability of 134 over 1,000. And of course, if you were to multiply the numerator and denominator of this break fraction by 1,000, you'd still have the 44 over 134, which when you do the division, you get 0.328 that we got on the previous slide. Okay, so there's another example of computing conditional probability. When you compute this conditional probability, you're just focusing your sample space on this second event. In this case, the event that the subject tests positive. This is now your new sample space. Okay. All right, so we'll leave it at that for now. Just as kind of a parting word, is that the probability of A given B is really not the same, usually speaking, as probability of B given A. Unless A and B are independent of each other. Otherwise, if A and B are not independent, then the probability of A given B and the probability of B given A, they are not going to be equal to each other. So it's incorrect to believe that they'll generally be equal to each other. The short answer is it's probably not true, except for when the events are independent. But to believe that probability of A given B and the probability of B given A are the same is what is termed the confusion of the inverse. And it's a mistake that you don't want to make. Okay? So with that, we are done for today. I've posted some new homework. I'm going to be looking at my calendar and thinking about when to start sending out the midterm exams. I'm going to have the midterm exam be on chapters 1 through 4. So I'm thinking probably next week is when I'll start sending out those midterm exams. So you need to start thinking about where you're going to take your exam in a proctored setting, whether it's at a DMAC campus or some other agreed upon proctor location. And if you are not taking your exam at a DMAC location and you haven't sent me your proctored form yet, you need to get that figured out soon. I'll send an email out on this a little bit later. Okay, folks, so take care. Have a good day. I'll post another lecture tomorrow, but I'm going to give you a 3-day weekend off because I'm going to be traveling on Friday. Okay? Have a good one. See you later. Goodbye.